This is SpaceTime Series 23, Episode 59. Coming up on SpaceTime, discovery of a twinkling heart to the Milky Way Galaxy, zooming in on fast radio bursts, and Skywatchers get treated to a penumbral lunar eclipse with an annular solar eclipse on the way. All that and more coming up on SpaceTime.
Welcome to SpaceTime with Stuart Gary.
Astronomers have detected twinkling radio emissions from what they think is the inner edge of an accretion disk around Sagittarius A star, the supermassive black hole at the centre of our Milky Way Galaxy. It's the first time these strange quasi-periodic flickers, which are thought to be happening very close to the event horizon, have been observed. The event horizon of a black hole is a point of no return, beyond which matter falls forever towards the singularity. A place of infinite density and zero volume where science's understanding of the laws of physics ends. Astronomers found these millimetre wavelength signals using ALMA, the Atacama Large Millimetre Submillimetre Array telescope in Chile. They were thought to be caused by the rotation of radio spots circling the supermassive black hole at an orbital radius smaller than that of Mercury's orbit around the Sun. A report in the astrophysical journal Letters claims they provide an interesting opportunity to investigate space-time in the extreme gravitational environment around a 4.3 million solar mass black hole. The study's lead author, Yui Iwata from Keio University in Japan, says Sagittarius A star has been known to occasionally flare up in the millimetre wavelength band. Using ALMA, the authors were able to obtain high-quality data for radio wave intensity variations of Sagittarius A star for 70 minutes a day over 10 days. They found quasi-periodic variations with a typical timescale of around 30 minutes, as well as slower hour-long variations. Sagittarius A star has been known to flare up in the past, not just in millimetre wavelength, but also in infrared and X-rays. However, the variations being detected with ALMA are much smaller than those previously detected. The authors suspect it's possible that these levels of very small variations are constantly happening in Sagittarius A star. We just haven't looked for them before. Of course, the black hole itself isn't producing any kind of emission. After all, it's a black hole. So the source of the emission is a scorching plasma accretion disk around the black hole. You see, matter falling to a black hole doesn't fall straight into the gravity well. Instead, it first rotates around the black hole, forming an accretion disk. The authors focused on the short timescale variations, finding that the variation period of 30 minutes would be comparable to an orbital period for the innermost edge of an accretion disk with a radius of around 0.2 astronomical units. An astronomical unit is the average distance between the Earth and the Sun, which is about 150 million kilometres, or 8.3 light minutes. Now, by comparison, Mercury, the solar system's innermost planet, orbits the Sun at a distance of 0.38 astronomical units. That's a semi-major axis of around 58 million kilometres. Considering the colossal mass at the centre of the black hole, its gravitational effect is also extreme in the accretion disk. So, this emission could well be related to some sort of exotic phenomena occurring in the vicinity of the supermassive black hole. The authors think that hotspots sporadically form in the accretion disk and then circle around the black hole, emitting strong millimetre wavelength signals. Now, according to Albert Einstein's special theory of relativity, the emission is largely amplified when the source is moving towards the observer at a speed comparable with that of the speed of light. And because the rotation speed of the inner edge of the accretion disk is quite large, this extraordinary effect would arise. The authors believe that this is the origin of the short-term variations in the millimetre emissions from Sagittarius A star. And if so, it could be affecting efforts to make an image of the supermassive black hole with the Event Horizon Telescope. That's because, generally speaking, the faster the movement is, the more difficult it would be to image the object. They believe the variation in the emission could be providing them with insights into the motion of matter in the accretion disk. In fact, they believe that they could witness the very moment material is being absorbed by the black hole with a longer-term monitoring campaign using ALMA. This is SpaceTime. Still to come, zooming in on fast radio bursts. And there's a bumper crop for Skywatchers. They've just been treated to a penumbral lunar eclipse, and they're about to be treated to an annular solar eclipse as well. All that and more still to come on SpaceTime. Astronomers are slowly uncovering more of the secrets of those mysterious cosmic explosions known as fast radio bursts. These massive blasts from deep space can release as much energy in a millisecond as our sun will produce in 80 years. Yet scientists have no idea what they are or what causes them. It's just a sudden, very powerful flash in the deep darkness of space, and then it's gone. The first fast radio burst, or FRB, described as the Lorimer burst FRB 010724, was detected back in 2007 in archival data originally recorded by the CSIRO's Parkes Radio Telescope back on July the 21st, 2001. Since then, most fast radio bursts have been detected through a re-examination of previously recorded data. But then, on January the 19th, 2015, astronomers at the Parkes Observatory recorded their first live burst. And as exciting as that was, it still offered no clues as to a possible cause. An early contender, supermassive black holes, were quickly ruled out when astronomers were able to localize fast radio bursts to the outskirts of galaxies and not near their central regions where these monsters lurk. And the fact that some but not all fast radio bursts can repeat means they also can't be caused by supernovae, the explosive deaths of massive stars. That's of course unless there are two different types of fast radio bursts, those that repeat and those that don't. With all this mystery surrounding their origins, fast radio bursts have become one of the hottest topics in astronomy today. Now, astronomers have successfully determined the exact location of 4 fast radio bursts, thereby allowing scientists to study their surrounding neighbourhoods. A report in the Astrophysical Journal claims that all 4 of these bursts came from massive galaxies that are forming new stars at fairly modest rates. In other words, galaxies very similar to our own Milky Way Galaxy. The observations were made using a specially designed transient detector attached to the CSIRO's Australia Square Kilometre Array Pathfinder Radio Telescope, ASCAP, located in outback Western Australia. ASCAP comprises 36 12-metre dishes located at the CSIRO's Murchison Radio Astronomy Observatory 800 kilometres northeast of Perth. Follow-up observations using some of the world's largest optical telescopes were then able to identify, image and determine the distances to their host galaxies. One of the study's authors, Dr. Shivani Bhandari from the CSIRO, says looking into the host galaxies of fast radio bursts provides unique insights into their origins. By knowing the type of galaxy the burst originated from and where in the galaxy it happened, scientists can rule out several of the more extreme theories put forward to explain their origins. Bhandari says it means these events could not have come from superluminous stellar explosions or from cosmic strings. However, models suggesting mergers of compact stellar objects like white dwarfs or neutron stars, or for that matter flares exploding from magnetars created by such mergers, still cannot be ruled out.
So fast radio bursts are flashes of radio waves that last for a couple of milliseconds, and they come from halfway across the universe, and they are extremely, extremely bright. So we have been using these amazing instruments called ASCAP, which is Australian Square Kilometre Array Pathfinder, to find these FRBs, and not only find them, but also localize them in the sky, which means that we exactly know their address, like we exactly know where they are coming from. And when we zoomed in to that particular address, which was given by CSIRO's ASCAP telescope, we found that these bursts are coming from the outskirts of massive galaxies. So using this hint, we can immediately rule in and start to rule out different models that could cause these FRBs. For example, now we know that because these FRBs were coming from the edges of the galaxy, we know that they prefer quieter suburbs rather than the densely populated downtown centers, which are the center of the galaxy. And we know that the supermassive black holes are monsters that live at the center. So just by knowing their exact location from within the galaxy, we can rule out that supermassive black holes have nothing to do with FRBs because they are just coming from outskirts of the galaxy. So this is one more step ahead in solving the mystery of what causes an FRB.
What do we normally find at the outskirts of galaxies?
So in the outskirts of galaxies, you have obviously stars, and those stars could be of any age group. So another interesting find that our research found was that some earlier work suggested that the FRBs could come from superluminous supernovae, which is a special class of exploding stars that are known to have very young sources. So this kind of galaxies that we have found in our sample are similar to our own Milky Way, which are all massive and luminous, and they are making stars, but in a very slow way. So they are very, very different to the galaxies which host such explosions such as superluminous supernovae. So in the outskirts of the galaxies, you find stars of different age groups. So it's more broader demographics rather than the stars which are in a galaxy that hosts some events such as superluminous supernovae.
Now, we've had so far two kinds of fast radio bursts. There have been the single events which only ever occur once, and then there have been repeating fast radio bursts.
Yeah, so the bursts that we have found using ASCAP have just repeated once. So we have looked back, we have went to that patch of the sky and looked for the repetitions, but for this sample that I have studied, we didn't find any repetition. So that's why we are claiming that these are the host galaxies of apparently non-repeating FRBs, and we have studied the very first sample of non-repeating FRB host galaxies.
With some fast radio bursts being repeaters, that has ruled out the possibility that they could be caused by a supernova explosion or something like that. But with non-repeating fast radio bursts, that must leave a whole gamut of possibilities still out there as to what's causing them.
If you look at a sample of the repeating FRBs, and for example, the one that are localized, like one of the repeating FRBs is coming from a tiny dwarf galaxy, which is making lots and lots of stars, and which is like the home in which events like superluminous supernova live. So, but our sample, we see that if we do an age analysis of the stars that we find in the fast radio burst galaxies, our sample, we see that there are stars of all ages. So we have ruled out the extreme ends. For example, in the sort of galaxies and the environments that we study for our non-repeating FRB sample, we see that the stars' ages are mixed. So there's nothing very young and no stars that are very, very old. So it's coming back to progenitors. So I think the fact that because the FRBs are not coming from the center, for our non-repeating sample, definitely rules out superluminous supernovae. It rules out the models of supermassive black holes. And because these FRBs are coming from the galaxy, we can also comfortably rule out cosmic string models.
Can we tell much about the chemistry of the stars involved, or are they too far away?
What do you mean by chemistry of the stars?
The spectra. I think that these galaxies are so far away, you can't really tell.
Yeah, so we have obtained, so using the optical telescopes, we have obtained the spectra for the whole galaxy. I'm not sure if it's possible to get a spectra for an individual star in the galaxy. So what we get from our telescopes are these photons that we are able to decode the message from, which reaches Earth coming from that galaxy. So you look at those photons, you look at the spectra, and from that spectra, you can see different emission lines and absorption lines. And using those emission lines, you can work out how far the galaxy is. So in our sample, we have found that these galaxies are about 2 to 5 billion light years away.
And they're in all directions in space?
Yes. That's true. So these FRBs are not coming from just one position. They are coming from random locations in the sky.
And the galaxies are all different? Or are they all disk galaxies? Are they all elliptical galaxies? Or are they all different?
Yeah, so that's a really interesting question. So another goal of our research was to find if FRBs, especially for our sample, which is non-repeating, are coming from a certain type of galaxy. But we found that these are coming from galaxies which are very similar to our own Milky Way. So they are massive, they are luminous, they are moderately making stars. There is nothing very super special about them.
Other than they're all a long way away.
Yes. And the fact that they are producing FRB in the outskirts. So something's going on there,
Where to next with this research? Where would you like to take it?
Yeah, so the next thing is, this has been a big step that we have been able to nail down the position of fast radio bursts and study a sample of their host galaxies. But definitely the next step will be to get enough of these hosts and accumulate enough statistics so that we can establish if FRBs really do prefer a specific type of galaxy or a preferred location. So we are on the right step, so we just need to make a bigger sample in order to root up more models so that we are finally narrowing down, and then during that process, hopefully we'll be able to nail down the exact progenitors or the exact sources that causes these fast radio bursts.
Are you pretty comfortable that there are two different sources of fast radio bursts, two different types, one that produces the single bursts and one that produces multiple bursts, the repeaters, or do you think we're still looking at a single type of burst, we're just seeing it from different perspectives?
So if you look at the burst itself, there are some properties which are very different from one-off bursts. So, for example, if you look at the repeating FRB, obviously it is seen to repeat. And there are other different features that are quite a bit different to when you look at the FRB itself. So if you are looking the signal itself, then there might be hints of two different classes. But if you look at the host galaxies, then it's quite confusing. Like, for example, we couldn't really say that repeating FRBs live in one type of galaxies and non-repeating FRBs live in another type of galaxies. When the very first repeating FRB was localized, that source is pretty unusual because that is in a tiny galaxy which is making lots and lots of stars. But when you look at the other host galaxy of the repeating FRB, that is very different. That is indeed similar to what we have in our sample. So if you are trying to approach that problem, whether there are two different kind of FRBs, just looking at their host galaxies and the environment, they're not super clear if there are two classes. But if you look at the FRB signal themselves, then there are some hints that could lead us to a conclusion that there might be two different classes and maybe two different production channels for FRBs.
That's very exciting, isn't it?
Yeah, it is indeed. And yeah, so when I started my PhD, I really wanted to, spend my whole PhD just trying to figure out the whole galaxies of these FRBs, because during that time, ASCAP was not running in that mode. And when I completed my PhD and I joined the ASCAP team, it has been a lovely experience to work with all the experts, and then to just be in a fast evolving field where things are happening at such a high pace, and then ASCAP is now leading the world in localization of non-repeating FRBs.
That's Dr. Shivani Bhandari from the CSIRO, and this is SpaceTime. I'm Stuart Gary. Still to come, Skywatchers witness a penumbral lunar eclipse, and there's an annual solar eclipse on the way as well. And later in the science report, the Lancet medical journal forced to retract its paper on hydroxychloroquine. All that and more still to come on SpaceTime. Skywatchers have been treated to a penumbral lunar eclipse, which appropriately happened to be the traditional strawberry moon, marking the start of strawberry season in the Northern Hemisphere. The 3-hour display was visible across Central and Eastern Africa, as well as Eastern Europe, both Western and Central Asia, while parts of Australia and Indonesia were treated to a partial lunar eclipse. A lunar eclipse can only happen during a full moon, when the Sun, the Earth and the Moon all line up exactly. The light from the Sun's then blocked out by the Earth from reaching the Moon. This happens between 2 and 5 times every year. Now, during a total lunar eclipse, the inner part of Earth's shadow, known as the umbra, falls on the face of the Moon, so that at mid-eclipse, the entire lunar surface is in shadow, well, at least the side of the Moon facing the Earth. And it's a spectacular sight, with light from the Sun refracted through the Earth's atmosphere and combined with particles in Earth's atmosphere, things like dust and smoke and pollution and volcanic activity. It all comes together to make the lunar surface appear red. And depending on the conditions, it can appear anything from pink or gold through to a stunning deep blood red. During a partial lunar eclipse, the Sun, the Earth and the Moon don't line up exactly, and so the umbra appears to only take a bite out of a fraction of the Moon. That bite will grow larger, but it then begins to recede again before reaching totality. Now, in what we've just experienced, a penumbral eclipse, again the Sun, Earth and Moon line up, but not exactly, so that only the more diffuse outer shadow of the Earth, known as the penumbra, falls on the lunar face. And that makes a penumbral lunar eclipse far more subtle and more difficult to observe, with only a slight shadow appearing during mid-eclipse. An important feature of lunar eclipses is that they always occur around 2 weeks before or after solar eclipses. And this sky show was a prelude to an annular solar eclipse which will take place on June the 21st, the day of the solstice. It'll start with sunrise over the Central African Republic, moving across the Congo and Ethiopia before crossing the Arabian Peninsula to southern Pakistan, across northern India and across China, eventually ending at sunset over the Pacific Ocean. A partial eclipse will be visible in North and Eastern Africa as well as southeastern Europe and across most of Asia. And the top end of Australia will also get a view in. People in Darwin getting about 57 minutes of partial eclipse, beginning at 17:33 in the evening local time, reaching its peak at 18:05 and concluding at 18:30. Now, if you happen to be at the northern tip of Cape York Peninsula, you won't miss out either. There'll be 22 minutes of showtime for you, starting at 17:52 local time, before reaching its maximum at 18:12 and then quickly concluding just 2 minutes later at 18:14. So, we've talked a lot about an annular eclipse. Exactly what is that? Well, because the moon's orbit around the Earth isn't completely circular but rather elliptical, occasionally the moon will be further away from the Earth, making it appear to be smaller. Too small, in fact, to cover the entire disk of the sun. So, instead of a total solar eclipse, the moon's passage across the face of the sun will create an annulus, a ring of fire, as light from the sun surrounds the dark moon, giving us a spectacular annular eclipse. This is SpaceTime. And time now to take a brief look at some of the other stories making news in science this week with a science report. The Lancet medical journal has been forced to retract its paper on a major study into the use of the drug hydroxychloroquine to help reduce the body's often accelerated immune response to the COVID-19 coronavirus. It's that immune response which often causes fatal outcomes. The study allegedly involved data collected from some 671 hospitals on 96,000 patients, including 81,000 controls, and 15,000 who were taking either chloroquine or its analog hydroxychloroquine, either with or without antibiotics. It concluded that those treated with any of the four combinations, that's chloroquine, hydroxychloroquine, and either of those drugs with or without antibiotics, ended up having a higher chance of death and heart rhythm problems compared to patients who were not given these medications. The conclusions triggered the immediate suspension of multiple trials into the use of hydroxychloroquine to treat COVID-19. The problem is, the Lancet findings were always very surprising. That's because hydroxychloroquine had been used safely for decades for malaria and for autoimmune diseases like lupus. Still, a second related hydroxychloroquine study, reported in the New England Journal of Medicine, was also retracted. The Lancet was forced to retract the article after some 150 doctors raised serious concerns about the data and questioned the study's conclusions, calling on all the peer-reviewed data to be published. Now, the study itself was based on data supplied by a Chicago-based company, Surgisphere, whose senior management just happens to include an artist, a full-time science fiction writer, and an aging fashion model. And suspiciously, the company had refused to supply its data to the scientist undertaking the peer review. You would have thought the alarm bells were ringing at the Lancet, but apparently they weren't. Mind you, this isn't the first major stuff-up by the Lancet. It's the same Lancet medical journal that was forced to retract the now infamous Andrew Wakefield study, wrongly linking the MMR vaccine with autism. Wakefield was eventually struck off the medical register over the study, and the paper was retracted in 2010. But the damage that caused still lives on today through the anti-vax movement, which still causes thousands of deaths and countless suffering around the world. A new study has confirmed that carbon dioxide levels now are higher than they've been at any time in the past 23 million years. The findings reported in the journal Geology dwarfs those previous warnings that carbon dioxide levels are worse now than they've been in a million years. The Mauna Loa Observatory in Hawaii is currently recording atmospheric carbon dioxide levels at 417.16 parts per million. The authors used fossilized remains of ancient plant tissues to produce a new record of atmospheric carbon dioxide spanning 23 million years of uninterrupted Earth history. They found that as plants grow, the relative amounts of the two stable isotopes of carbon, carbon-12 and carbon-13, changes in response to the amount of CO2 in the atmosphere. Archaeologists in Sri Lanka have discovered the earliest known use of a bow and arrow outside Africa. An international collaboration between Griffith University, the Max Planck Institute, and the Sri Lankan government unearthed evidence for the bow and arrow technology in the island's tropical rainforests. A report in the journal Science Advances describes the discovery and the analysis of arrow points made of bone, which apparently were used to hunt tree-dwelling animals such as small monkeys and squirrels. Well, I'm sure you've all seen that now famous video of the hero house cat attacking a pit bull that was trying to savage a young child in the driveway. And you've all heard stories about dogs rescuing their owners. I'm not just talking about Lassie saving Timmy when he falls down a well. But would your dog really want to save your life if you were in trouble? Well, a new study by scientists at Arizona State University says yes, they really would like to save your life, but only if they knew how. Scientists tested 60 dogs by placing their owners in what to the dog appeared to be a dangerous situation. Now, in reality, it was just a box with a sliding door, and the dog would need to nudge or slide open the door in order to rescue their owner from inside. Now, the owner inside the box had to yell for help and sound distressed, but not call the dog by name. Of the 60 dogs in the test, 20 responded by rescuing their owners. Now, that 33% might not sound impressive, but it's actually very impressive when one considers two key factors. First was the dog's desire to help its human, and secondly, the dog's ability to work out how to rescue its human. Now, in a control test, researchers simply dropped food into the same box, and 19 out of 60 dogs in that test managed to open the box to get to the food. Now, of those 19 dogs, 16 also rescued their owners. So, 84% of the dogs capable of opening the box did so in order to save their humans when it counted. In a second control test, the owners were placed inside the box but didn't yell for help. And in that test, 16 out of 60 dogs still went to the box and opened it in order to be reunited with their bosom buddies. The authors found the fact that the dogs opened the box more often when they thought their owners were in distress than during the quiet test showed that rescuing couldn't be solely explained by the dogs wanting to be near their owners. They also found that during the distress test, the dogs were also in far more stressed states when their owners were distressed. They would bark more, they'd whine more, and generally whimper. All in all, the authors say it shows dogs really do care about the welfare of their humans. Psychologists have noticed a new trend that's becoming especially apparent among COVID-19 coronavirus deniers. It seems people rejecting scientifically sound public health advice about the coronavirus pandemic seem to mostly fit into one of three very specific categories. Those which display a specific political viewpoint, those who are medically uninformed and are unwilling to learn, and those who have a tendency to believe in conspiracy theories. And as Tim Mendham from Australian Skeptics explains, there can be overlap between the three categories.
This is a study actually from a psychology publication which says that there are three types of deniers of what they call a scientifically sound public health response to coronavirus. There's a political partisan approach that won't allow people to accept it. There's the medically uninformed, which is basically ignorance. And there's those with a tendency to believe in conspiracy theories. Now, there's a lot of overlap between the three, and I can think of a number of people that I know in the public sphere who certainly are uninformed, politically partisan and conspiracy theorists. It's a problem actually that trying to overcome all of these things, politically partisan obviously, especially with areas like climate change and those sort of areas, but also with the pandemic. Anything that requires a strong government input or control worries people who are of a frame of mind. So it doesn't matter what the situation is. If they fear a government is sort of controlling our lives, they'll be against it. There's the medically uninformed, I don't know, I can't see it, therefore it must not exist, sort of scientific ignorance, quite frankly. Whether that's their fault or someone else's fault, it's no one's fault that they're ignorant, they just haven't been taught it. And ignorance creates fear, and therefore fear creates rejection. So if you do not understand the science, it's too hard, sort of, I'll close my eyes and stick my fingers in my ear and it'll go away.
That's the same argument used by climate change deniers, isn't it?
It's very much the same, actually. Yes, it's not a problem, blah, 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 blah. I'm not listening, it'll go away.
La, 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 No.
And then there are those who tend to believe conspiracy theories. And what this sort of particular article points out is that's on the left and on the right, depending on what particular theory you're talking about. This suggests that the anti-vaccine movement is mainly on the left and the anti-climate change is mainly on the right. So no one's particularly unprone to these beliefs. It's when you combine all three that you're really in trouble. And then you sort of think, well, how do I deal with it? This particular article says you're trying to sort of persuade people is going to be difficult because there is this underlying philosophy that underpins and that undermines everything you want to sort of inform them of. It's running uphill in many cases to combat.
Yeah, but you're challenging their very belief system, aren't you?
Yeah, and it's a very fundamental belief. It doesn't matter what you're talking about, which particular area. There was a fundamental belief system that underpins everything, every decision they make. And trying to sort of tear that down or to change that or to influence that is very hard, almost impossible. Some people you just got to give up on. But what this article then says is that perhaps saying to people you've got to change your mind is not going to work. Perhaps you've got to make regulations. And you say, forget your ideas, this is what the law is going to be. And you've got to lump it, which of course reinforces
what they're thinking.
Yeah. That's right, yeah.
I think the idea is that you've got to try and look at it from their point of view and ask them why they believe what they believe and what their evidence is, and then try to slowly pick away at it that way. That's the only thing I can think of that might work.
Well, this comes down to the other thing about how much scientific information can you give people to make them change their mind. And if they believe that any information is coming from a corrupt source, be it science or politics or public sector or whatever, they're not going to listen to it and they're not going to act upon it. It's bashing your head against a wall for people who are of a particular mindset. The trouble is there are people in influence who have those mindsets, and they are encouraging others just by being there. And how do you deal with it? This is the why of these belief systems is the ultimate question that skeptics keep asking. It's not so much the what, that's obviously an issue, but why do people believe in these things, and what is their basic philosophy that encourages them to believe these things, and that when one area falls flat, they'll move to another area because of this underlying philosophy of their attitude. This is the $64 question, is why people believe, and if you could really get to the crux of that, which people are trying to do, as I say, political point of view, lack of information and tendency to believe conspiracy theories, people are looking into all these things and trying to find out why the hell these things are happening. And maybe it's just a facet of normal human life. Who knows? Trying to overcome that and educate people. Well, education and critical thinking is the way to overcome it, and showing people not what to believe, but how to assess beliefs. And if you can do that to people from an early age, which you can, and the Australian government curricula in education all stress critical thinking in almost every subject you can think of, if you really implement that, you have a population that makes up its mind based on evidence rather than on political bias, ignorance, or conspiracy, you're well on your way to actually having a society that can actually make it at least an informed decision.
That's Tim Mindham from Australian Skeptics. And that's the show for now. SpaceTime is broadcast on Science Zone Radio by the National Science Foundation in Washington, D.C., and through both iHeartRadio and on TuneIn Radio. Or you can subscribe and download SpaceTime as a free podcast through Apple, Stitcher, Bytes.com, Pocket Casts, SoundCloud, Spotify, YouTube, Audio Boom, Podbeam, Android, Castbox, from SpaceTimeWithStuartGary.com, or from your favorite download podcast provider. You can help support the show and the work we do by visiting the SpaceTime online shop and grabbing yourself a few goodies, or by becoming a SpaceTime patron, which gives you access to commercial-free double-episode versions of the show, as well as bonus audio content and other rewards. Just go to our Patreon page through SpaceTimeWithStuartGary.com for all the details. If you want more SpaceTime, check out our blog, where you'll find all the stuff we couldn't fit in the show, as well as loads of images, news stories, videos, and things on the web I find interesting or amusing. Just go to spacetimewithstuartgary.tumblr.com. That's all one word and in lowercase, and that's Tumblr without the E. You can also follow us through @StuartGary on Twitter, at SpaceTime with Stuart Gary on Instagram, through our SpaceTime YouTube channel, and on Facebook, just go to www.facebook.com/SpaceTime with Stuart Gary. SpaceTime is brought to you in collaboration with Australian Sky and Telescope magazine, your window on the universe.
You've been listening to SpaceTime with Stuart Gary. This has been another quality podcast production from Bytes.com.